Hello everyone, welcome to physics classes. I am Sarabdeep Kaur Sidhu here. So today our topic is energy bands in solids. So for this article we will plot a graph. I plotted a graph between interatomic spacing, that is R, and relative energy of the electrons. Clear? So we know that from Bohr's atomic model, we know that in an atom electrons have well defined energy levels. Clear? So in a crystal there are a number of atoms, they are interact with each other. Clear? In a crystal there are a number of atoms. Suppose there are n atoms, and in a crystal an atom is influenced by a large number of neighboring atoms. So due to this reason, electrons in the outermost shells of the atoms are forced to have different energies from the energy of electrons in an isolated atom. Means when atoms are close to each other, then there are a number of forces between them, attractive and repulsive also, so their energy levels modified. Clear? Clear? Than an isolated atom. So, or we can say that energy levels of outer shells of the atoms get modified. That there is a little modification in the energy level of the electron, the inner shells of the atoms. So to understand this modification of energy levels, we consider a single crystal of silicon. So suppose silicon has n atoms. If these have n atoms and these atoms are brought closer from infinity to form a crystal, and each atom is associated with the lattice side. Now see at the diagram what is. So the plot or the diagram is between the interatomic spacing, that is R, and the relative energy of the electrons. So silicon atom have atomic number 14. So the electronic configuration is 1s2, 2s2, 2p, 6, then is 3s2 and 3p2. Clear? And when we also called it a tetravalent atom, and when there are n silicon atoms, we consider, suppose there are n silicon atoms, then that 1s, 2s, 3, 2p, these are here, and this is 3s and 3p. 3s is also 2, 3p 2. Clear? So this is a diagram. Now we consider the R is equal to A, interatomic spacing. R is equal to A is the actual spacing. This is the actual spacing between the silicon atoms. Clear? And we consider at R is equal to, we will discuss at R is equal to A, R is equal to B, R is equal to C, and R is equal to D. Process of splitting of the energy levels in silicon. Clear? So first we consider at R is equal to D. We will R is equal to D, or D is very greater than A. A is the actual interatomic spacing. Clear? When R is equal to D, and that we can say interatomic spacing of the atoms is very large, then there is no interaction of atoms with each other. And energy level of all the n atoms will be identical, or we can say discrete and distinct, corresponding to electronic configuration of silicon. Clear? So electronic configuration of silicon, what it shows? It shows that two outer subshells of silicon, that is 3s and 3p, contain 2 electrons each, 2 here, 2 here. Thus in silicon, 2n electrons completely filled 2n possible energy levels of 3s state, and 6n possible states. For 3p energy level, there are 2n electrons, clear, and 6n states. So out of these 6n states, 2n are filled and 4n are empty, and all 3p levels have same energy. Clear? Because we have n silicon atoms. We have n silicon atoms. So here is 2n electrons. Clear? 2n electrons, 2n states. Here is 2n electrons but 6n states. 4n states are empty, and all the 3p states have same energy. So this is just like an isolated atom. This reason. Clear? And when interatomic spacing lies between C and D, between C and D, that is reason A. Clear? There is no visible splitting of energy level. Clear? Same, provided C that is very greater than A. Clear? Then when R is equal to C, now at this point R is equal to C, then interaction between electrons of 3s and 3p levels becomes appreciable, or we can say energies of 3s and 3p levels of each atom of silicon starts changing here, or we can say splitting of levels, energy levels starts. At this distance there is no change in the energy levels of the electrons in the inner shells. So just for 3s and 3p, splitting of levels just starts at R is equal to C at this point. Okay, ji? Then when R is less than C and greater than B, means we can say between B and C. So between B and C, then energies of 3s and 3p levels becomes interaction. What? Energy of 3s and 3p gets slightly changed, or we can say this is a reason B. Clear? And instead of a single 3s or 3p level, we get 2n energy levels corresponding to 3s and 6n energy level corresponding to 3p level of an atom. All these levels are closely packed in a very small energy range. So such a set of closely spaced energy level with continuous energy variation, energy variation is called energy band, So this reason. Clear? And when R is equal to B, what will happen at R is equal to B? R is equal to B, which is greater than A, then the energy gap, this is the gap, energy gap between 3s and 3p levels disappears. That is the reason C. The gap disappears. If a gap disappears, we get a continuous distribution. Continuous distribution, 8n energy levels. 8n energy levels, 4n and 4n. So in this case it is not possible to distinguish between the electrons belonging to 3s and 3p subshells. So we can't differentiate between the electrons, that electron is of 3s level or of 3p level, because here is a continuous distributed electrons are. So out of 8n energy levels, 4n levels are filled and 4n levels are empty. So 4n levels are filled and 4n levels are empty. Clear? So here gap disappears. Then is R at R is equal to A. So at R is equal to A. Then at R is equal to A, band of filled energy levels gets separated from the band of empty energy levels by an energy gap that is called the forbidden energy gap. So filled separated from the empty. You see, no allowed energy levels can exist in the forbidden energy gap. So highest energy band that is filled or occupied by the valence electron is called the valence band, from this point to this point. And highest, or we can say next empty loud band, next empty, not highest, next empty loud band is called the conduction band. So this is valence band, this is conduction band. So we know that according to Pauli exclusion principle, the two electrons with opposite spin can occupy an energy level in a band. So energy levels are occupied by atoms in such a way that total energy is minimum. That's if energy is minimum, system is stable. So and then Fermi energy or Fermi level. So highest energy level that is occupied by the free electrons at 0 Kelvin, is called the Fermi level, and the energy corresponding to that level is called the Fermi energy, So this is all about valence band, how they form valence band, conduction band, and the gap between valence band and conduction band is called the forbidden energy gap. Clear? Now in a simple way, this diagram is also explained in a very simple way. For example, this is the case of a silicon, and also we can take another examples. For example, we take sodium crystal, sodium atom in a solid. There are number of sodium atoms. So sodium atom have a atomic number is 11. So configuration is 1s2. Clear? This is 1s, then is 2s, then is 2p. Clear? Then is after 2p there is a 3s, 1s2, 2s2, 2p6 and 3s1. And if we combine, we have n atoms of a sodium, sodium, then what will happen? In a crystal or in a solid, the energy levels of the electrons in a level are not equal. So this, for example, in 1s, if one electron of one atom have energy this, other have this, other have this, so on at the, so they form a band, they form a not bond, band. In this way, this is 1s, 2s, 2p, but this is less modified band, lower bands. Clear? Now number of quantum state for 1s is 2n, for this is also 2n, for this is 2n, 2n, and for 2p this is 6n, and for 3s this is 2n. This is the states, this is the energy levels or bands, and number of electrons for 1s, that is because n atoms, 2 electrons, so 2n. Number of electron here is also 2n. For number of electrons for 2p, this is 6n, because 6 into n, and for this is n only, because only there is one electron. The n, if there are n atoms, then n electron. This is number of electrons. Then last filled band, which is the last filled band, that is 2p. 2p level is last, because if we take for a single atom, then these are the levels, and if we take for a number of atoms, the energy levels of the electrons, they are not same energy levels, so they form a bands. And this is the upper filled, because this is fully filled, completely filled, not upper, completely filled. This is completely filled, so this becomes valence band, and this is partially filled, not completely, and this is called conduction band. And it become at low temperature, only at low temperature, and when we increase the temperature, then electrons from this valence band goes to this conduction band, and the gap between these is called the forbidden energy gap. So highest energy band, which is energy band which is filled, that is called a valence band, which is completely filled, and the lowest energy band, which is not completely filled, is called the conduction band. This is all about the valence band, conduction band, and forbidden energy gap. Then is about the difference between valence band, conduction band and forbidden gap. So first we can say valence electrons are present in the valence band, we know that. And in a conduction band, what is present? Electrons are rarely present in the conduction band. At 0 Kelvin only valence band is completely filled and conduction band is empty. When we rise the temperature, then electrons are shifted from valence band to conduction band, and here there are no electrons, never present. Clear? And for valence band, this band is never empty, partially or completely filled. Completely filled at 0 Kelvin, and when temperature rises, the electrons jump from valence band to conduction band, and this is either empty or partially filled, and this is no completely empty. And third difference is electrons in this don't contribute to electric current. The electron contribution only are valence that are the electrons in the conduction band. So here electrons contribute to the electric current when we apply electric field or external field to the this. Clear? And here is this energy gap, Eg, which is required to shift an electron from a valence band to conduction band. When electron wants to jump to a conduction band, then they have energy equal to or greater than the forbidden energy gap, and this gap is different for different conductors, for insulators, and for we can say semiconductors. For example, for germanium it is 0.7 electron volt, and for we can say silicon it's 1.1 electron volt for semiconductor, silicon and germanium. And also for insulator about 6 electron volt, and for conductors different depending upon the type of the conductors, which type of conductor we are considering. Then also we can define, then last we define valence band is the highest energy level band which is completely filled. Clear? At low temperature. This is very important, at low temperature. Clear? This is the lowest energy band which is not completely filled. So this is all about valence band, conduction band and forbidden energy gap. In the next lecture we will discuss about metals, insulator, conductors. ठीक है जी, thank you very much.